Hello, everyone. Welcome to this week's Green Bank Observatory Community Zoom. It's good to be back on campus. Some quick announcements before we get started. So summer maintenance has started and we're moving track covers today, and we're going to be working on foundation. We do have some unexpected observing time available in the next couple weeks. We were going to put some, replace some of the wheels, but the wheels are ready, but the bearings are not. So the manufacturer has a delay in providing us with the bearings. So in any case, we'll do that replacement later in the season. But that means that we have some nighttime observing and weekend observing available. So if you have projects and you're interested in observing, please enable your project so that we can get you on the schedule. The disposition letters for Green Bank proposals are coming out very shortly. They're due out this week. We should have the results posted on the web on Friday. Very nice turnout for proposals this semester. We have a lot of large proposals requested. We had a 6-to-1 oversubscription in terms of hours requested versus hours available. So lots of demand for the telescope, and we had some really good proposals and covering quite a wide range of scientific topics. Next week, we have the NRO GBO Internal Science Symposium. There will be a Zoom link for that. We'll get that posted on our website. If you're interested, just let me or Jay Lockman know, and we can get you that information. It's Monday and Tuesday next week. It'll go from like 9 to 5. Looking forward to seeing the scientific staff's latest and greatest research. So with that, I'll hand it over to Jay Lockman, who will introduce today's speaker.
Thanks very much, Jim. Today's speaker is Jack Orlowski-Scherer from the University of Pennsylvania, and he'll be speaking on a survey of point sources in clusters of galaxies and other updates from Mustang 2. Let me remind everyone to submit your questions using the Q&A button at the bottom of the screen, and we'll get to them at the end of the presentation. And also, this presentation is being recorded for future viewing, so you should be able to access it through the GBO website in a day or so. Take it away, Jack.
Thanks for having me, Jay. Thanks for the introduction. It's good to be here. Let me go ahead and share my screen and just confirm that everyone can see that.
Yes.
Looks great. Okay, great. So as she said, I'm Jack Orlowski-Scherer. I'm a staff scientist at the University of Pennsylvania. I work on Simons Observatory as well as Mustang 2 and ACT. Simons and ACT both CMB observatories, Mustang 2 instrument on the GBT. And I'm going to be talking today primarily about a recent paper published using M2 data. The link to the paper is here. And I'll give some other quick updates about science that's in the works, so that in the pipeline with Mustang 2, as well as some potential instrumental upgrades. So I am presenting on behalf of a lot of people on the M2 team, primarily Simon Dicker, who's the actual lead of this work. He's on vacation right now, so I'm more or less presenting in his stead. Karen Sarmiento, a student here at the University of Pennsylvania, and also Brian Mason, a staff scientist at NRAO. Plus the entire M2 team. So just a little bit of scientific motivation. What are clusters of galaxies, and why do we care about them? I'm sure plenty of people here are familiar with them, but just going back over them. So clusters of galaxies are what they sound like. They're clusters of galaxies that all live in the same potential well and were formed out of the same cloud of baryonic matter. They're the largest structures in the universe. And in particular, they're the largest structures that have had time to form in the lifetime of the universe. If you take the growth formation rate and you run the clock forward from the Big Bang, there's only so much structure you can build up in the finite lifetime of the universe, and clusters of galaxies are the largest in that hierarchy of scales. And so that gives them the not the unique, but the property that they can test, that they provide stringent tests of lambda CDM cosmology or any cosmological model. And in particular, because they're the largest structures, you don't need to observe a lot of them to start putting rigorous constraints on lambda CDM. In fact, if you have a significantly large enough cluster, that one cluster alone can be in tension with lambda CDM. So what I'm showing over here on the right is a galaxy cluster called El Gordo. It's called that because El Gordo means the fat one. It's an extremely massive cluster that was detected first by the Atacama Cosmology Telescope and the SC effect. It lives at a fairly high redshift, and the initial mass estimates for this cluster were so high that this cluster by itself actually was above the limits at the time of what we thought was possible to assemble in lambda CDM. The mass estimates for this cluster have subsequently been revised down, and it's no longer in tension with lambda CDM. But the point, the fundamental point remains that you can do a lot with relatively little. And in addition to their power as cosmological probes, clusters are also, as the largest structures in the universe, we like to say laboratories for astrophysics. They have the highest energy processes in the universe. And so if you're interested in large, high-energy astrophysical processes, galaxy clusters are a great place to look for those. In particular, most galaxy clusters have a very large AGN in their brightest central galaxy. That's what you're seeing here in a Chandra image. You're actually primarily seeing the AGN there. And then these are just optical views on the clusters. So, like I said, a single cluster can constrain cosmology. More generally, what we want to look at is the abundance of clusters. So this is the number of clusters above a certain mass scale as a function of that mass scale. And that abundance function is, constrained directly by the underlying cosmology. So if you have a certain cosmological model, it'll make a prediction for what this chart should look like. Now, these particular models are very outdated. They're not, I think, all ruled out currently. I just chose this plot because it's illustrative. It's the most illustrative plot I could find at this point. So the black is a real measured abundance function of clusters, and these dotted lines are various lambda CDM cosmologies with different growth sigma 8s and different matter densities. And you can see that, as we vary these parameters, the models make different predictions for this abundance function. You can see that none of these are particularly good fit set of data, but that's sort of fine. This is an independent probe of the cosmology of our universe. So, very hot right now to try and understand the growth of structure in our universe. And this provides a complementary probe to other probes like, the CMB, direct observations of the CMB, for example. So how do we actually go about detecting them? There's a lot of ways that you can do it. The way that we on the Mustang 2 team do it is via what's called the Sunyaev-Zeldovich effect. So the SZ effect is a spectral distortion of the CMB, the cosmic microwave background. It's caused by inverse Compton scattering of CMB photons off of the intracluster media. And one interesting interesting nuance to this effect is that it's redshift independent. The strength of this effect is the same or nearly the same at all redshifts. And so you have a redshift independent probe of clusters. So you're only limited by the mass of the clusters. Now, of course, the earlier you go in the universe, the lower mass clusters tend to be. They haven't had time to get big yet. And so functionally, you see less as you go to higher redshift. But for a given mass cutoff, it's independent. And this is what it actually looks like. The solid lines here are TSC for various energy or various temperature ICMs. And you can see the sort of key point here, frequencies on the top x-axis is probably the easiest to read, is that when we go to about 90 gigahertz, which is the Mustang 2 observing frequency, we observe a deficit in photons. And so when we map a cluster with GBT, what we see is essentially a cold spot that corresponds to the ICM in the cluster. Two other things I want to point out. One, in general, not with in general, CMB experiments are relatively low resolution, and that'll come into play later in the talk. Specifically, they're blind to what's going on in the cluster. So if you have point sources, for example, they can't distinguish the point source from the cluster itself. And this relation requires calibration. There's not a first principles way of turning this distortion strength into the mass of the cluster, and instead we have to rely on a mass calibration. That's what this plot is showing you here. This is a example of a YM scaling relation calibrated using X-ray data. So M here is the mass of the cluster, and Y is this Compton Y parameter. It doesn't matter. It's essentially a parameter that parameterizes the SZ distortion. So you need to get this calibration correctly. And so the issue with this calibration, as you can see on this chart, is that there's quite a bit of scatter in this. And so if you want to do good cosmology, you gotta get that scatter down. So there's a lot of sources of this scatter. Some of it is just, there's intrinsic scatter. Some of it is due to there's an assumption of self-similarity here in the pressure profile that can be violated. And some of this scatter, I think about 20-ish% of the scatter is due to contaminating sources in the point sources in the clusters. Okay. So I mentioned that we use CMB surveys to find clusters. The cluster catalog that we'll be talking about today that's relevant was created by the Atacama Cosmology Telescope, which I'm also a member of. It's a 6-meter off-axis Gregorian telescope. It's located, as the name suggests, in the Atacama Desert. It has a 3-degree field of view, so it has a large field of view. It's for doing surveys of large portions of the sky. It observes at 90, 150, and 220 gigahertz, although 90 and 150 comprise by far the bulk of the data volume that ACT has produced. There are upcoming low-frequency observations. And I didn't actually mention it here, but the resolution is about 1.2 arc minutes. Now, the typical angular scale of a cluster on the sky is about 2-ish arc minutes, give or take, which is very close to the resolution of ACT, and that is not a coincidence. The resolution of ACT was selected to make it well matched to finding clusters. It also makes it good at doing CMB science, but that particular number was settled on because it allows you to detect clusters very well. However, it's not, you don't really resolve clusters. There are only about 2 to 3 resolution elements across for ACT. And so any of the details that are inside a cluster are lost. And so you can take the ACT frequency maps and you can make cluster catalogs out of them. The most recent one is called the ACT DR5, stands for Data Release 5 cluster catalog, which was, you can find all the details here in this really great paper by Matt Hilton. It comprises just about 4,200 SC selected clusters, all of which are optically confirmed. It's the largest homogeneous sample of SC selected clusters to date. It covers about 13,000 square degrees. The full ACT survey is about 18,000 square degrees, but there are cuts for clusters around areas of high galactic contamination, for example. And it has significant overlap with optical surveys, which in particular is nice because it allows you to do weak lensing mass calibration, which I'll talk about briefly later. This is what the actual footprint of the ACT catalog looks like. So you can see DS here, Hyper Supreme Cam. I forget what purple is, some other optical survey. And you can see the coverage there. And up here on the top right is just a neat little plot showing the actual real space distribution of our clusters. So the smaller bulge is this top patch, and the larger one is that bottom one. So how do you actually find these clusters? Well, remember I said the TSC effect is play the video, is a spectral distortion. Well, these clusters have a characteristic spectral shape. They have the shape of the TSC spectrum, and they also have a characteristic spatial shape. There are a variety of models for these, but they all tend to look similar in real space. And so what we do is we take our CMB maps and we apply a matched filter to them, where the filter is matched both in frequency to the SC spectrum and is spatially to the sort of typical shape of a cluster. And so that you can see here, this is what our raw data looks like. Now, all these red points are not clusters. Those are point sources. The clusters show up as cold spots. So you can see there goes one right now. And yeah, that's definitely one right there. There goes another cold cluster. And so this is the sort of thing that the matched filter picks out. And again, just to reiterate, these matched filters insensitive to the fine details. So this is what one of the matched filters looks like. It's kind of like a Gaussian, but not really. It's not actually a Gaussian, but it kind of looks like one. And so you can see the response here. The response is strongest at the center of the cluster, obviously, and it tapers off. And one sort of key but non-intuitive feature of this filter is that due to ringing in the filter, it actually has negative response out at a couple arc minutes. So out below about 1.8 arc minutes, it starts to go negative, which reaches a minimum at around 2.5 arc minutes at nearly a 10% negative relative response. And physically, these scales actually still correspond to the galaxy cluster. So you're talking about the outskirts of the galaxy cluster out here, but it is still part of the cluster. And so stuff that lives out here, if it emits, will end up in the ringing of the filter. And so that leads to a somewhat unintuitive result. So if you have a point source living in a cluster, most obviously it can suppress the measured Compton Y of the cluster by living near the center, right? So if you remember back a couple slides, the SC effect is a deficit at 90 and 150 gigahertz. So if you have a positive source, it infills that deficit, which reduces the inferred Compton Y. Less intuitively, if that source lives in the outskirts of the cluster, it can actually boost the cluster Compton Y, and so you can end up overestimating the mass of the cluster. Now, you can skirt around a lot of this using weak lensing. So recently, CMB maps have reached a sufficient depth that instead of relying on the Compton Y parameter to get a mass estimate for the cluster, you can use stacked weak lensing, where you stack up a whole bunch of clusters and measure the weak lensing signal to infer the mass. And that is unbiased, certainly in terms of point sources, but in generally unbiased, which is great. But there's still two remaining issues here. One, both of which come down to we can't detect individual clusters via their weak lensing signal, only stacks. And so one, to detect clusters still requires a TSC-based approach. And two, to do an initial sorting of clusters into mass bins to do that stacking approach, you need a mass estimate, which again is supplied by the TSC. So you still have the source of bias where one, you're picking clusters based on their TSC mass, and two, you're sorting them into bins on their TSC mass. Now, both of these effects you can, of course, marginalize over in your analysis. The CMB cosmology people are very good at marginalization, but you need to know how to do that marginalization, right? You need to understand what your bias is in order to marginalize that out. And so we use Mustang 2 to essentially get after how bad is the biasing of point sources in clusters selected via the TSC effect. So probably a lot of people here are familiar with Mustang 2. You're certainly familiar with the GBT. Mustang 2, it's a 90 gigahertz instrument on the GBT. It's very high resolution for a TSC instrument at 9 arc seconds. It has a very high sensitivity and a relatively large instantaneous field of view that make it very well suited to mapping clusters. Again, this is not an accident. Mustang 2 was designed to do many science cases, but one of the primary ones was mapping clusters. And so the first sort of study of this we did was using an ad hoc sample. The Simons paper, Dicker 2021, looked for point sources in 30 clusters that had been already observed. So this was archival M2 data. These were clusters that had been observed for other science cases. And we went back and looked through them for point sources and then made an estimate of how bad the mass bias was in those clusters due to those point sources. Now, that's all well and good. You don't have to spend GBT observing time. That's great. We get science for free. But there's a pretty big drawback here, which is that the Dicker 21 sample is very biased, right? It's biased towards interesting clusters, right? People had to submit and then get approved for observing time. And so, these tend to be clusters that are in some way interesting. So high redshift, ongoing mergers, stuff like that. And both of these we know strongly affect the distribution of point sources. In particular, there are more point sources at high redshift, or at least are more active at high redshift. And ongoing mergers also tend to be associated with more AGN activity. The physical interpretation here is sort of that you're feeding more gas to the AGN. These observations are also really deep because they were going after faint science cases, but they're not uniform depth, right? The depth was just set by whatever the science constraint of that particular observation was. And so, now we have a non-uniform, highly biased sample. So it's good for getting a handle on whether this is a problem or not. So here's what we've plotted here on the right is one of those clusters is Able 2052, plotted in SNR. It's a really large cluster, well above the ACT mass completeness limit, but it's actually absent from the ACT cluster. And that's because there's a big honking point source in the middle of it, which is so big it's actually completely infilled the signal from Able 2052. This cluster is invisible to ACT, and going deeper won't help because the problem is just that the point source flux is like equivalent to the SC deficit flux, not technically a flux, but it shows up but because you have the resolution with Mustang 2, you can go in and you can excise this point source and recover the cluster. And just to give you an idea of the resolution, this cyan circle over here is the ACT resolution. I'm actually sure not what frequency. It looks like that's probably 90, but I'm not 100. No, that's probably 150. And this over here is the Mustang 2 beam. So you can see the enormous improvement that Mustang 2 makes. How do we actually do that? The way we do that is by taking a cluster. We take real data of a cluster from ACT data. Sorry, we take ACT data. So it's ACT frequency map at 9150. And we inject an artificial point source into it, right? Point source, it's a Gaussian, very easy to put a fake point source in your data. And then what we do is we mess around with the parameters of that point source, the amplitude, where it is in the cluster, and its spectral index. And then we pass those maps through the real pipeline that's used to extract the mass from the cluster, the ACT, the Matt Hilton's pipeline. And that results in you then get a effective mass for the cluster, and we know the real mass of the cluster that we put in. And so you can figure out the fractional change in Compton Y due to that point source. So what you're seeing here is a plot that shows the effect of decentering a source. So we've taken a source and just same spectral index, same inherent flux, and just moved it in and out radially. And you can see this basically looks like the matched filter. I think it's exactly what it is. It should be exactly the matched filter convolved with the beam. And then we do a similar thing with spectral index. So because Mustang 2 is monochromatic, right? We don't get the 150 gigahertz flux, which also goes into the ACT SZ mass estimation. And so we have to figure out, based on the spectral index, what's the change in response. And you put those two together, and you can make a plot like this, where you essentially, if you have a source flux and you have it at a certain radius, and you assume a spectral index, then you can figure out what the delta Compton Y is. So here are the results of that. Most of the clusters that we were able to process, so 18 out of 24 have 24 of the 30 clusters have point sources, of which 18 of those 24 have a radio counterpart, meaning we went and looked in radio catalogs, and they have a match at radio frequencies. And the net effect is shown here in this cumulative histogram. So on the x-axis here, we have the percentage change in y due to the point source. So over here means you have a 30% deficit. Here means you have no change whatsoever. You get the right mass. This is what happens if you don't have a point source. And then over here, excuse me, you have increases in inferred mass due to the point source. And then that's cumulative fraction. The black line here shows the results of the M2 sources. And so, yeah, you can see the whole histogram, but like the rough figure of merit is that about 10% of our clusters show 10% decrease in Compton Y. We also see about 5% that show an increase in Compton Y, which is, I believe, exactly one cluster. The population level effect here is about 1 to 2%. 1 to 2%. So essentially, that you can think of it as being like, on average, on average, if this sample was representative of the ACT cluster catalog, which it is not, you would guess that the ACT clusters are about 1 to 2% low in mass compared to reality. In addition, because this sample came from proposals, some of these clusters that were observed were TSC selected, and some of them were X-ray selected. And by comparing those two sort of cross populations, there's some evidence for bias between those two populations. The X-ray clusters show a lot more contamination than the SC ones. That's perhaps not surprising. If you have a lot of contamination, it's not going to show up in an SC survey, but X-ray instruments are insensitive they see the point sources, but they're not biased by them. Both the X-ray, the cluster signal, and the point source signal are positive, so it doesn't make the clusters invisible in the X-ray. So as I said, one of the major downside of the Dicker 2021 work was that you have this very highly biased sample of clusters. And so we put in a proposal to do a uniform and a heterogeneous sample. We proposed to observe all ACT clusters above a certain declination and in a certain right ascension range. This proposal this is about I think it's exactly 300 clusters. This proposal was accepted and was observed from about early 2022 through mid 2023. The SC catalogs so this is based on the ACT cluster catalog, which has a mass limited selection function, so it's unbiased in principle, with the caveat that it is biased in terms of if you have a very bright point source and you don't see the cluster, which is, of course, important because that's exactly what we're trying to get at. So little limitation to the work there. Of the 300 we proposed for, we were able to observe 243. And of those 243 clusters, 24 are identified as having sources. The typical depth in our map is about 200 microjansky. That's deep enough that if you to identify a source that would have a significant biasing effect on the mass. So for a typical size cluster, a 200 microjansky source is going to end up producing about a 0.5% bias in mass. So at that point, you're under the statistical, uncertainty on the cluster mass. So this is sort of a well-motivated noise. And just showing here in red, those are the areas. All the clusters in those boxes were observed. So what do these counterparts? Pardon me. For the 24 detected clusters, are there counterparts at other frequencies, and what do they look like? The answer is we do have counterparts. They're mostly radio. So we searched for counterparts in a number of radio and IR catalogs going all the way from gigahertz and even down into a couple hundred kilohertz through the submillimeter and all the way out into the true infrared. Of the 24 sources that we detected, 75% of them have at least one radio counterpart. Some have multiple. I think 2 have multiple. In general, so while they do have radio counterparts, in general, those radio sources do not do a good job of predicting the Mustang 2 flux. What I mean by that is if you take the radio flux and you take the radio spectral index and you just do that scaling all the way up to 90 gigahertz, you end up with a flux estimate that's wrong. In general, it's lower, although we do find actually a couple where, in general, the flux estimate is low, although we do find a couple estimates where it's high.
Jack, if you could summarize now, that would leave us a couple minutes for questions.
Oh, I'm sorry. Yeah, absolutely. So they don't do a great job of predicting the flux. We also find IR counterparts, but they all have negligible emission by the time you get to 90 gigahertz. We also are missing a lot of point sources. So essentially, this is the completeness limit, and these red dots are showing you the inferred, the radio inferred flux for all these point sources. So basically, every red cross to the right of this dashed line should be detected. As you can see, only a very small number of them have. And the takeaways from this are that the M2 counterpoints are basically all radio sources, most likely AGN, although with one frequency, we can't really tell. And both the discrepancy in fluxes, inferred fluxes, and the large number of missing radio point sources indicate that there's probably a spectral break. At some point, there's in these sources somewhere between 3 and 90 gigahertz. And this has been observed before. So this is just confirmation of this sort of earlier effect. In terms of the cosmological results, it's a much lower bias than the previous work. Only the 10% of clusters in this sample only have about 2.5% deficit in delta Y, which is down a factor of 4 from the previous sample. But notably, there is a relatively large component with positive delta Y. So the takeaway here is that the cosmological effect is small but non-negligible. And you can marginalize over it using simulations, with the caveat that the simulations don't do a great job of capturing the excess, the sort of boosted clusters. So you should probably marginalize over the real distribution from our work there. So I'm sorry, I didn't realize, what was is this only a half an hour talk?
It's a 15-minute talk.
I got completely the wrong time schedule for that. I'm
Sorry.
so sorry.
Yeah.
I'll go ahead and cut it there then.
Well, listen, thank you very much. We'll keep going for a few more minutes if people have questions, and please submit them through the Q&A button at the bottom of the screen. I will ask the first question. You made a comment offline earlier about a possible follow-up to Mustang 2.
Yes. Yeah. So the idea here very quickly is Mustang 2 is great, but it was limited by the technology at the time. We could cram a much larger receiver into the turret at GBT, about twice as big, and get roughly, actually much more than twice as good science results. So we're currently considering 2 proposals. One is a new receiver that we're calling Wicked. This would lead to about a 25 times increase in mapping speed, would be polarization sensitive, and would also come with a cryogenic half-wave plate to mitigate atmospheric effects. The more conservative route is an upgrade to the existing receiver, where we replace the detector arrays and add a cryogenic half-wave plate, but use the same limited field of view receiver. As said, would have a similar, somewhat higher mapping speed. The big advantages here would be we would add polarization sensitivity and also split the band. Currently, we just have one band that fills the entire 90 gigahertz atmospheric window. So think about cutting that in half and having 2 sub-bands. If you have strong opinions about the science cases for and the merits of one over the other, please reach out to us. We are writing grant applications. So if you feel strongly about the, the science applications of this in particular, reach out to us and let us know. We'd love to hear from you.
Thanks very much. We have time for one question, and we have a question. Can you speak for a minute on the high Z infrared selected clusters studied with Mustang 2?
The high Z, they're not part of this sample. We have, so the sample that we looked at is strictly SZ selected. I actually don't know. Yeah, I'm actually not familiar with our IR selected clusters. Sorry. Yeah.
Okay, thank you very much. We're going to have to end it there. Let me thank you very much, Jack, for speaking today on this interesting topic, and which seems to have quite a future for the GBT. As I mentioned, this is being recorded, and so you'll be able to see it within a day or so through the Green Bank Observatory website. Please join us in 2 weeks for our next talk, which will be the 100th in this series, and will feature Scott Ransom talking about the marvelous millisecond pulsars in the globular cluster Terzan 5. That's on May 22nd, and we hope that you can join us then. Thanks very much and goodbye.